everyone. So there's a link I posted on our D2L page that's linked to this compound interest. So it's a periodic table of oxidation states. Let me just zoom in for a second. It's kind of cool. So it tells you the oxidation states that are known, so all of the ones that are colored. Oxidation states that are not known. So if we look at magnesium for a second, okay, look at magnesium for a second. So 0, +1, +2 are the ones that are options. The most common states are kind of have this like dot around it. Can I zoom in a little bit more? Yeah. So, okay, apparently I cannot move this thing when it's zoomed in. Okay, so 0, 1, 2 are observed oxidation states. 0 and +2 are the most common ones. So, and it has it for also all of the elements in the periodic table. So some of them you're going to see have quite a variety of numbers that it can be. So carbon can go anywhere from -4 all the way up to +4, and they're all common. It happens quite a bit. So chlorine is another one. Sulfur is another one. So if you want to keep this handy with you, I would not rely on this. Like I said, I would go through more the rules and figuring out what the sum of your compounds have to be. But if you're not sure if that state exists, this is kind of a cool periodic table to use. Okay, so that link is on D2L. All right, so let's get to our practice problems. So we have here the different molecules or ions or ionic compounds that we want to assign. So the first one we actually did already. So for water, we know hydrogen is +1 and then oxygen is -2, right? And so remember that these have to add up to 0. So for cesium peroxide, okay, so cesium is a regular ion. So it's in group 1. So you would just assign it a +1, right? So this is really, right? This is really cesium +1 and then peroxide -2, right? So if it helps you, if you know it's an ionic compound, metal, nonmetal, or a polyatomic ion, break it up so you can see it easier. Okay, so oxygen, when it's in a peroxide, is equal to -1 because each one is basically -2 plus the 2 cesiums add up to 0. Okay, carbonate. So oxygen here is going to be -2. It's not any exception. So when you have -2, our oxygens are -6, which means our carbon would have to be +4 in this case in order for that to add up to -2. Okay, sodium, right? I'm going to break this up so we can see this a bit easier. So this is sodium dichromate, right? So sodium would be a +1. It's a regular ion. Oxygen, this is not any exceptions here, so it's just -2. So if we know oxygen's -2, and there are 7 of them, that's like -14. And then each chromium has to be +6 in order for this to totally add up to -2, right? So it's kind of a little bit of algebra involved here. If you want to be more formal and say like let X represent the oxidation state and figure it out that way, you can. It's kind of like mental math. They're very straightforward. You're just basically adding, subtracting, very, very easy multiplication. Okay, so we have -14, so you know the other side has to be +12, so you have to think, okay, well, what does each one have to be to add up to +12, right? So the answer there is, of course, +6. Okay, barium hydride. So barium is a regular ion, which is +2, it's in group 2. Hydrogen, because this is in a metal hydride, this would be -1. NH4 plus, actually, we did this example already. So this is -3, hydrogen is +1. They all add up to +1. S8 is, you may or may not know this, but this is the elemental form of sulfur. So this would actually be assigned a value of 0. Okay. Aluminum sulfate. So again, you can break this up into the individual ions if you wish. So we know aluminum is +3, oxygen is -2, and sulfur in this case would have to be +6 for all of this. So all of this altogether will add up to 0. Like I said, I just find it easier to look at the individual polyatomics when doing this. Okay, so what happens in a redox reaction? We've already mentioned this. So you have oxidation and reduction. And of course, how are you going to know this is happening? You look at what is changing in the oxidation numbers. That's actually why we do it. So when you assign oxidation numbers to the reactants and products in a reaction, you can see, well, what's changing? If there is an increase in oxidation number, so let's say we went from +2 to +4, right? That means that this has lost 2 electrons, right? So it's becoming more positively charged. If you have a reduction, you should see a decrease, right? So meaning it's gaining electrons. So if we have something going from +2 to 0, in this case, it would have gained 2 electrons, right? So by seeing the change in the oxidation numbers, that allows us to predict what's happening, right? So let's do an example. So let's say we had zinc plus HCl. We'll do like a single displacement reaction here. Doing zinc chloride and hydrogen gas. Okay, and we need to balance. Okay, so when you're assigning oxidation numbers, you assign it for every element that's here. So we're going to assign it for zinc, we're going to assign it for H, we're going to assign for Cl, zinc, Cl, and then H. Okay, following the rules we just finished doing. So zinc is in its elemental form, so that's 0. Hydrogen's +1, chlorine is -1. These are regular ions. Chlorine is -1, it's a regular ion. Zinc is +2, and hydrogen is a 0 because it's in its elemental form. So if we look to see what is changing, zinc, for example, is going from 0 to +2. So it's losing 2 electrons in the process of this reaction. If we look at chlorine, chlorine is not changing. So that means actually nothing is happening to chlorine. However, hydrogen is going from +1 to 0. So that means that hydrogen is actually gaining an electron, right? Each hydrogen atom is gaining an electron. So that tells us what's going on. So zinc is the one losing electrons, so that means that's oxidizing, and hydrogen is the one gaining, which means it's reducing, right? So like by assigning the oxidation numbers properly and seeing what's changing, you can predict what the reaction is that's happening, right? So here's another example. So if we were to assign oxidation numbers, I know it's a little bit dark here, but hopefully you can see this with the bright red. So let's say oxygen is -2, so chlorine here would have to be +5, right? It all has to add up to 0, to -1. I2 is 0, chlorine is -1. Now iodate's a polyatomic, so oxygen's -2, and iodine is +5 here. So oxidation, we're going from 0 to +5, right? So that means it's losing 5 electrons, right? Each iodine is losing 5 electrons. Chlorine is going from +5 to -1. So in this case, each chlorine is actually gaining 6 electrons. So when you're looking at this and assigning the process, even though you have chlorine as part of chlorate, chlorine is actually the substance that is doing the reducing, okay? But because it's in a polyatomic ion, like it's kind of clustered together, they will usually say chlorate is being reduced. Like, but however, we know it's because the chlorine within it. Okay, so we've already talked about this. So how are you going to remember which one is which? So you can say Leo the lion is Gur, losing electrons is oxidation, or gaining electrons is reduction. And there's also oil rig. So oxidation is the loss of electrons, or reduction is the gain of electrons. I don't care which one you use. You just have to be able to know what's happening. Okay? All right, so oxidizing and reducing agents. So these terms are, it can kind of get confusing, but an agent is something that is helping, okay? So, you know, like FBI agent helps to solve a crime or something. So the agent is like the helper. So when something is an oxidizing agent, that means that it is helping oxidation. If something is a reducing agent, that means that it is helping reduction. So in order to help that process, it does its own thing. Okay, so what I mean by that is, if I am losing electrons, okay, and I am oxidizing, I am going to help reduction, because if I did not lose electrons, there would be no electrons for that thing to gain electrons, right? They're a coupled process. Each one helps the other. So like, for example, if I'm gaining electrons, that's going to help oxidation to happen because there's somewhere for those electrons to go. Okay? So this is a nice process. So let's say you have A and B as your reactants. So if A is the one that is losing electrons and it's oxidizing, so see how the electrons went on to B? So B gained the electrons and A lost them, but they help each other. So the one that was oxidized is a reducing agent, sometimes say Ra, and the one that was reduced was the oxidizing agent. So in other words, we just remember that it's always the agent of the opposite process. Oh Lord, there's an ambulance going by. Okay, so we'll do one last part with the final practice problems of this section.